What if Jupiter is not a planet, but a machine? A planetary engine so vast, so deep, that what we see on its surface is only the faintest shadow of something far more powerful beneath. For more than 3 centuries, one storm has raged across Jupiter's face: the Great Red Spot, a swirling vortex large enough to swallow Earth whole. A crimson wound in the clouds that has refused to fade, refused to collapse, refused to behave like any storm we understand. On Earth, hurricanes rise, intensify, and die within days. Even the strongest systems lose energy once they move over land or colder waters. Our atmosphere has limits, boundaries, friction, interruption. Jupiter has none of those. For centuries, astronomers assumed the Great Red Spot was a surface phenomenon, a massive atmospheric vortex spinning high in the upper cloud layers. Then NASA's Juno spacecraft arrived, and everything changed. When Juno entered orbit around Jupiter in 2016, it carried instruments capable of doing something no mission had done before. It could measure gravity with extraordinary precision. It could peer through clouds using microwave radiometers. It could map magnetic fields with unprecedented sensitivity. It was not there to take pretty pictures. It was there to weigh the invisible. And what it discovered beneath the Great Red Spot stunned scientists. The storm was not shallow. It did not skim the surface. It plunged downward between 300 and 500 kilometers into Jupiter's atmosphere. Let that sink in. On Earth, nearly all weather occurs within a thin shell called the troposphere, roughly 10 to 15 kilometers thick. That entire region, the full vertical stage of our climate, would fit comfortably inside the uppermost fraction of Jupiter's storms. The Great Red Spot extends 20 to 30 times deeper than Earth's entire weather system. It is not a storm sitting on top of the atmosphere. It is a storm rooted within it. And that realization forces a question. If storms on Jupiter reach that deep, what exactly are they anchored to? To answer that, we need to let go of something fundamental: the idea of a surface. On Earth, there is a clear boundary between sky and ground. Air above, rock below, weather above us, geology beneath us. Jupiter does not offer that comfort. Its outer layer appears striped, bands of bright creams and dark browns wrapping around the planet like colossal brushstrokes. These are cloud belts and zones sculpted by jet streams racing at unimaginable speeds. But those clouds are not floating over land. They are floating over more atmosphere. Jupiter is composed of roughly 90% hydrogen and about 10% helium, the same ingredients that make up stars. It is, in a sense, a failed star. A world that gathered enormous mass but never acquired enough to ignite nuclear fusion. Its atmosphere is not a thin veneer. It is the planet. The uppermost cloud layers are arranged in 3 primary tiers. At the top sits ammonia ice, bright, pale, reflecting sunlight into space. Beneath that lies ammonium hydrosulfide, giving the clouds their darker yellow-brown hues. Deeper still, water clouds form in regions where pressure and temperature allow droplets to condense. On Earth, water clouds form a few kilometers above our heads. On Jupiter, water clouds form dozens of kilometers down. And below those layers, there is no solid ground waiting. There is no sharp boundary where atmosphere ends and interior begins. Instead, pressure increases. Gradually, relentlessly. Descend a few dozen kilometers, and the environment begins to transform. Hydrogen, the simplest element in the universe, begins to behave in ways no human has ever experienced directly. Pressure builds to levels far beyond anything on Earth. Wind speeds exceed 600 kilometers per hour, nearly twice the speed of the most violent terrestrial hurricanes ever recorded. But unlike Earth, where jet streams snake unpredictably across hemispheres, Jupiter's rapid rotation stretches these winds into stable, colossal ribbons that wrap entirely around the planet. Jupiter completes a full rotation in just under 10 hours. That speed generates immense Coriolis forces, twisting air currents into long, organized bands. Instead of chaotic turbulence, Jupiter's atmosphere becomes structured, ordered, divided into alternating belts of rising and sinking gas. Storms do not simply drift randomly. They are guided, stabilized, trapped within invisible corridors shaped by rotation itself. And this is where the scale becomes almost impossible to grasp. Some of Jupiter's storms are wider than Earth. The Great Red Spot spans more than 16,000 kilometers across. Entire continents could vanish inside its swirling vortex, yet its true power lies not in its width. It lies in its depth. Juno's gravity measurements revealed that beneath the visible clouds, the storm's mass anomaly, a subtle gravitational signature, extends hundreds of kilometers downward. That means the vortex is not merely spinning in sunlight. It is connected to layers where heat rises from deep within the planet. Because Jupiter does something extraordinary, it emits more heat than it receives from the sun. Think about that. At its distance, sunlight is weak, pale. Yet Jupiter radiates nearly twice as much energy as it absorbs. That extra heat is not borrowed from the present. It is left over from the past. A remnant of gravitational contraction that began billions of years ago when the planet first formed. As Jupiter accumulated mass, gravity squeezed it inward. That compression generated enormous heat, and even today, the planet has not finished cooling. Jupiter is still shedding primordial energy, still glowing faintly from its violent birth. So when storms plunge 300 to 500 kilometers downward, they are tapping into reservoirs of internal heat. They are not powered solely by sunlight, as Earth's weather systems are. They are driven from below, from the inside out. At those depths, pressure begins altering hydrogen itself. Under extreme compression, hydrogen transitions through exotic phases. Its molecules are forced closer and closer together, their behavior shifting in ways that blur the line between gas and liquid. Deeper still, thousands of kilometers below, hydrogen will eventually become something even stranger. Metallic. But we are not there yet. For now, imagine descending through endless clouds, deeper and deeper, where sunlight fades into dim amber haze, where temperatures rise, where pressure crushes any known material. The storms above are not isolated phenomena. They are surface expressions of a deep convective engine. On Earth, convection is limited. Warm air rises, cool air sinks. The cycle repeats within narrow vertical boundaries constrained by solid ground. Jupiter has no ground to interrupt the flow. Its convection columns can stretch thousands of kilometers downward and forming vast spiral pathways through darkness. Energy does not circulate in short loops. It travels through planetary-scale rivers of gas. This is why the Great Red Spot has endured for more than 350 years of recorded observation, and likely far longer. It is not a temporary disturbance. It is part of a planetary metabolism, a self-sustaining system anchored in heat that has been radiating since the dawn of the solar system. And that forces a realization that unsettles something in our intuition. We tend to think of gas giants as simple, balls of swirling clouds, featureless worlds without surfaces, without structure, without complexity beneath the haze. But Jupiter is not simple. It is layered, dynamic, alive with physics under conditions we cannot replicate fully on Earth. Its atmosphere does not sit on top of a world. It merges seamlessly into it. There is no moment where you could say, "Here is the sky, and here is the planet." It is all one continuum, an ocean of hydrogen extending tens of thousands of kilometers downward. And if storms reach 500 kilometers deep, if jet streams stretch tens of thousands of kilometers around, if internal heat radiates outward from ancient gravitational collapse, then perhaps what we are looking at is not weather. Perhaps we are looking at the outer ripples of something far more immense, a planetary engine running beneath the clouds. But storms are only the first clue, because when Juno flew over Jupiter's poles, it found something even stranger: chaos, arranged in perfect geometry. And that is where the mystery deepens. When Juno first flew over Jupiter's North Pole, scientists expected turbulence. They expected disorganized storms colliding in violent confusion. What they saw instead looked almost deliberate, almost designed. At the very top of the planet, where sunlight barely grazes the clouds and temperatures plunge into shadowed cold, Juno's cameras revealed something no one had predicted: an octagon. 8 massive cyclones, each between 4,000 and 7,000 kilometers wide, arranged in a near-perfect circular pattern around a central storm. Imagine hurricanes the size of continents. Now imagine 8 of them, standing side by side, not merging, not tearing each other apart, not drifting randomly, but locked into position like pillars surrounding a throne. At Jupiter's south pole, the configuration changes, not 8, but 6 colossal storms orbiting a central vortex. No symmetry between hemispheres, no neat mirror image, and yet the same defining characteristic: stability. Over more than 5 years of continuous observation, Juno saw almost no change in their arrangement. The storms did not collapse. They did not spiral inward. They did not dissipate. They endured. On Earth, when 2 cyclones approach one another, they interact chaotically. Sometimes they merge in what meteorologists call the Fujiwara effect. Sometimes one absorbs the other. Sometimes they destabilize entirely. But Jupiter does not follow those rules, because Jupiter rotates faster than any other planet in the solar system. A full rotation in just 9 hours and 55 minutes. That speed generates an immense Coriolis force, a rotational effect that deflects moving air into curved paths. On Earth, the Coriolis effect shapes hurricanes and jet streams. On Jupiter, it dominates them. Air masses are twisted into powerful vortices that behave less like drifting storms and more like anchored structures. Think of each cyclone as a column of gas plunging hundreds of kilometers downward, not a flat swirl on a surface, but a vertical pillar rooted deep in layers of rising heat and descending currents. Juno's microwave instruments detected that these polar cyclones extend far below the visible cloud tops. Their internal structure is 3-dimensional, reaching into regions where temperature and pressure gradients form invisible thermodynamic boundaries. That depth is crucial. On Earth, storms lose strength when they encounter land. Friction disrupts circulation. Energy supply is cut off. Jupiter has no land, no surface to interrupt the flow. Its atmosphere transitions gradually into denser fluid layers below, allowing vortices to anchor themselves in continuous convection columns. These polar storms do not merely spin, they are embedded in the planet's energy system. And the geometry itself is astonishing. 8 storms in the north, 6 in the south. Why not 7? Why not 10? Why these numbers? Computer simulations suggest that when multiple cyclones form in a confined rotating region, they naturally arrange themselves into polygonal patterns to minimize interference. It is a kind of atmospheric self-organization. Chaos reorganizing into structure. Under extreme rotation and immense scale, disorder does not dissolve. It stabilizes. The storms at the poles orbit a central cyclone, maintaining fixed distances as if gravitationally choreographed, where each one repels the others just enough to prevent merging, while the Coriolis force confines them within a stable ring. It is a balance of pressure gradients, rotation, and deep convection, a dynamic equilibrium sustained by forces invisible to the eye. Juno also detected temperature contrasts between the cores and edges of these vortices. The centers tend to be colder at the cloud tops, while warmer air circulates around their peripheries. Those thermal differences reinforce the structure. The storms feed off gradients. They persist because energy continues to rise from below. And here is what makes this discovery profound. For centuries, humans assumed that chaos is inherently unstable, that storms are temporary by nature, that turbulence inevitably decays. Jupiter contradicts that intuition. On this world, chaos can endure. On this world, energy flows are so vast, so continuous, that storms become architectural, permanent features sculpted by physics rather than erosion. The contrast with Earth is stark. Our planet is a world of short cycles. Storms form and fade. Weather patterns shift. Even climate oscillates within geological timescales. Jupiter is a world of atmospheric endurance. Its immense size and lack of a solid surface allow systems to persist for decades, centuries, perhaps millennia. The North Pole's octagon is not a coincidence. It is the visible signature of deep planetary rotation interacting with endless convection. And that brings us to an even more unsettling realization. If Jupiter's poles can organize chaos into geometric stability, if continent-sized storms can remain locked in position for years, then what other invisible forces are shaping this planet from within? Because the polar vortices are only the outer expression of something much larger, something that does not merely move air, and something that moves matter itself. When Juno began mapping Jupiter's magnetic field, scientists expected something relatively simple: a dipole. North and south magnetic poles aligned roughly with the planet's rotation axis, similar to Earth, but stronger. They were wrong. Jupiter's magnetic field is nearly 20,000 times more powerful than Earth's. But more importantly, it is uneven, irregular, lopsided. Instead of a smooth global field, Juno detected blotches, intense magnetic concentrations in some regions, and unexpectedly weak zones in others. One of the strangest regions lies near the equator. Scientists call it the Great Blue Spot, a broad, drifting patch of magnetic anomaly unlike anything seen on our planet. It is not fixed. It moves, slowly shifting over time, as though it mirrors currents flowing deep beneath the atmosphere. Magnetic fields do not drift randomly. They are generated by moving conductive material. On Earth, molten iron in the outer core circulates, generating our magnetic dynamo. On Jupiter, there is no molten iron ocean like ours. There is something far stranger. But before we descend that far, consider the implications of what we have already seen. The storms are deep. The poles are geometric. The magnetic field is asymmetrical. All signs point to a planet that is not static, not layered neatly, but dynamically intertwined from top to bottom. Energy rising from the interior feeds storms. Rotation organizes them into stable formations. Deep currents distort magnetic fields. Everything is connected. And the deeper Juno looked, the clearer one truth became. Jupiter is not merely a gas giant. It is a system. An engine powered by internal heat, structured by rotation, and threaded by magnetism. The polar storms were not the final mystery. They were the warning. Because beneath those geometric vortices lies a realm where hydrogen itself transforms, where pressure becomes so extreme that matter changes identity, where invisible rivers of metal flow in darkness, and where the true source of Jupiter's immense magnetic power resides. To understand that, we must go deeper still, beyond storms, beyond clouds, into a region where the light of the sun never reaches, and where hydrogen becomes something no one on Earth has ever touched. Beneath Jupiter's storms, beneath the geometric cyclones locked at its poles, beneath the belts and zones that wrap around the planet like painted ribbons, there is a boundary. Not a solid surface, not rock, not ice, but a threshold where matter itself begins to change identity. When Juno started mapping Jupiter's magnetic field in detail, scientists expected strength. What they did not expect was chaos. Jupiter's magnetic field is the most powerful planetary field in the solar system, nearly 20,000 times stronger than Earth's. It stretches millions of kilometers into space, carving out a magnetosphere so vast it would appear larger than the moon in our sky if we could see it. It traps radiation. It accelerates particles to near-light speed. It shapes the space environment around the planet like an invisible fortress. But it is not smooth. It is not symmetrical. It does not behave like a simple bar magnet buried inside a planet. Juno's magnetometers revealed something strange, blotches of extreme intensity, regions where the magnetic field is far stronger than expected, and other regions, weak, distorted, misaligned. One anomaly stood out above all others. Near Jupiter's equator lies a drifting magnetic region known as the Great Blue Spot. It is not fixed in place. It moves, slowly, measurably, or over time. Magnetic fields do not wander unless the material generating them is in motion, and that motion cannot come from the upper clouds. It must originate far below. To understand why, we need to descend thousands of kilometers beneath Jupiter's visible atmosphere. As pressure increases with depth, hydrogen, the simplest, lightest element in the universe, begins to compress. At first, it behaves as a gas, then as a dense fluid. Then, something stranger happens. Under pressures millions of times greater than Earth's atmospheric pressure, hydrogen's electrons begin to move freely. Its molecular structure breaks down. It becomes electrically conductive. It becomes metallic hydrogen. This is not metal in the way we think of iron or copper. It does not look shiny. It does not form solid bars. It is a fluid metal, an ocean of electrically conducting hydrogen under crushing pressure and extreme temperature, and it occupies an enormous fraction of Jupiter's interior. Imagine a layer tens of thousands of kilometers thick, a vast global sea of liquid metal. Now imagine that sea in motion. Jupiter rotates in under 10 hours. That rapid spin, combined with internal heat rising from deeper layers, drives convection within the metallic hydrogen region. Hot material rises, cooler material sinks, the entire layer churns. And because metallic hydrogen conducts electricity, those motions generate electric currents. Electric currents generate magnetic fields. This is Jupiter's dynamo. But unlike Earth's relatively stable molten iron core, Jupiter's metallic hydrogen layer is far larger, more turbulent, and more complex. Juno's data suggests that the dynamo region may not be uniformly distributed. Instead of a neat spherical shell generating a symmetrical dipole field, the metallic hydrogen may form swirling vortices, enormous twisting flows of conductive fluid. These vortices stretch, distort, and warp the magnetic field. That is why Jupiter's magnetism is lopsided. That is why the Great Blue Spot drifts. It is not a scar on the surface. It is the signature of deep internal currents reshaping the planet's magnetic identity in real time. This realization shattered older models. For decades, sea scientists assumed Jupiter had a relatively simple interior structure, a dense solid core at the center, surrounded by metallic hydrogen, surrounded by molecular hydrogen, surrounded by clouds, layered, predictable, ordered. Juno complicated that picture. Gravity measurements revealed that Jupiter's mass distribution does not match what a compact solid core would produce. If a heavy, well-defined rocky nucleus sat at the center, its gravitational signature would appear in the planet's moment of inertia. Instead, Juno detected something diffuse, spread out, faint, as if heavy materials were not concentrated tightly at the center, but smeared over a vast region. And this led to one of the boldest hypotheses in planetary science. Jupiter's core may have been shattered. More than 4 billion years ago, when the solar system was still young and chaotic, protoplanets were colliding constantly. Worlds were forming through violent mergers. Computer simulations suggest that a planetary embryo, possibly as large as Earth, may have slammed directly into Jupiter during its early formation. The impact would not have destroyed Jupiter. It was already too massive. But it could have disrupted its forming solid core, breaking it apart, fragmenting it, mixing rock and metal into the surrounding hydrogen layers. Over time, those fragments may have dissolved partially into the metallic hydrogen ocean, creating what scientists now call a fuzzy core, not a compact nucleus, but a diffuse region extending perhaps 30 to 50% of Jupiter's radius. That means the core could span 20,000 to 35,000 kilometers, wider than the diameter of 2 Earths placed side by side. Not solid, not sharply defined, but blended into surrounding layers. If this is true, our Jupiter is not a planet with a stable heart. It is a world still mixing itself from within, and this has profound consequences for its magnetic field. Because if heavy elements are distributed unevenly through the metallic hydrogen region, convection patterns will also be uneven. Electric currents will concentrate in some areas more than others. Magnetic strength will fluctuate across hemispheres, which is exactly what Juno observes. The magnetic field is not static, or it changes over time. It responds to internal flow. This means Jupiter is not a finished system. Its dynamo is evolving, its interior currents are shifting, and its magnetic personality is being rewritten slowly, year by year. Now consider what this implies on a larger scale. Jupiter's magnetic field is so strong that it traps immense radiation belts. Charged particles accelerated within its magnetosphere create an environment so hostile that spacecraft must shield themselves heavily just to survive close approaches. The radiation around Jupiter is intense enough to damage electronics within hours. Juno itself follows a highly elongated orbit designed to minimize time spent in the harshest regions. This magnetosphere interacts with Jupiter's moons. It strips particles from Io's volcanic plumes. It induces electrical currents in Europa's subsurface ocean. It shapes auroras at the poles far more powerful than Earth's northern lights. And all of that begins deep below the clouds, in a realm of metallic hydrogen rivers, twisting in darkness. But here is the deeper philosophical shock. We tend to think of gas giants as passive. Massive, yes, but simple. Featureless spheres of gas with little complexity beneath. Juno has proven the opposite. Jupiter is not a passive ball of hydrogen. It is a colossal electromagnetic engine. Its storms are linked to deep convection. Its convection links to metallic hydrogen. Metallic hydrogen links to electric currents. Electric currents generate magnetic fields. Magnetic fields shape space around the planet. Every layer influences every other. There are no isolated systems here, only feedback loops, only interaction, only motion. And perhaps most astonishing of all, we are witnessing this in a world that formed 4.5 billion years ago. A planet that should have cooled, should have settled, should have become static, but hasn't. Jupiter still radiates excess heat, still drives deep convection, still reshapes its magnetic field, still evolves, and if its core truly dissolved long ago, if heavy elements are still mixing, then Jupiter may not be finished forming. It may still be reorganizing its internal structure. A planet in slow motion transformation. And this forces us to reconsider something fundamental. If the largest planet in our solar system does not have a clean, solid core, if its interior is fluid, dynamic, unstable, then the textbook image of planetary structure, neat layers stacked like an onion, may be an oversimplification. Jupiter is not layered simplicity. It is blurred boundaries, a gradient world, a continuum of pressure and transformation. But magnetic fields and metallic hydrogen are only part of the story, because Juno discovered something else, something that bridges the atmosphere above and the metallic ocean below. Lightning, not like Earth's lightning, but bolts erupting from depths no one expected, and strange ammonia waterstones falling like bullets through darkness. Weather phenomena that do not exist anywhere else in the solar system. If metallic hydrogen is the heart of Jupiter's engine, then these phenomena are the sparks flying upward from it, and they reveal that Jupiter's atmosphere is not isolated from its interior. It is connected, in ways we are only beginning to understand. Lightning begins in darkness. On Earth, lightning forms high within thunderclouds, where water droplets and ice crystals collide. Electrical charges separate over a few kilometers. The atmosphere breaks down. A bolt flashes. It is dramatic, but it is shallow. Jupiter does not do shallow. When Juno began detecting lightning discharges, scientists were surprised by their intensity. These were not faint flashes scattered across upper cloud layers. They were powerful electrical bursts, some visible from orbit as bright slashes cutting through the planet's night side. And they were forming far deeper than expected. For decades, planetary models assumed that convection strong enough to produce lightning occurred mainly in upper water cloud layers. But Juno's microwave radiometer revealed something else. Liquid water exists deeper within Jupiter's atmosphere than we once believed, far below the bright ammonia clouds, below ammonium hydrosulfide, within regions hidden beneath thick layers of hydrogen gas. There, under immense pressure, water droplets collide violently. Electrical charges build. Lightning erupts, not just kilometers above a surface, but tens of kilometers down inside a vertical ocean of gas. The implications are enormous. Because lightning requires energy gradients, it requires motion, it requires instability, and instability means active convection, which means Jupiter's deep atmosphere is not stratified and calm. It is alive with vertical transport. But lightning was only the beginning. There was another puzzle. For years, astronomers noticed that ammonia, one of Jupiter's primary atmospheric constituents, was mysteriously depleted in upper equatorial regions. Models predicted certain concentrations. Observations did not match. Where was the ammonia going? Juno helped answer that question with one of the strangest discoveries ever made in planetary meteorology. Mushballs. Inside powerful deep storms, water and ammonia can mix under pressure and low temperature to form partially frozen, dense, slushy objects, not pure ice, not simple droplets, but ammonia-water hailstones. These mushballs grow heavy, and when they do, gravity takes over. They fall, hundreds of kilometers downward, carrying ammonia with them into deeper atmospheric layers before melting under increasing pressure and temperature. This process explains why upper layers appear ammonia-poor. The ammonia is being transported downward mechanically, locked inside falling stones. Nothing like this exists on Earth. On our planet, hail forms within thunderstorms and falls back to the surface. But on Jupiter, there is no surface. Mushballs do not strike ground. They descend into deeper gas layers, redistributing chemistry vertically across enormous distances. It is a bridge between atmospheric layers, a mechanism connecting top clouds to depths invisible to sunlight, and it reveals something critical. Jupiter's atmosphere is not a simple stratified blanket. It is an open system. Mass and energy are constantly exchanged between upper and lower regions. Convection columns rise thousands of kilometers. Ammonia and water cycle through deep pathways. Electrical storms ignite far below, where we once believed weather could exist. Everything moves, and when Juno combined atmospheric data with gravitational measurements, an even more dramatic picture emerged. Deep inside Jupiter, material flows extend thousands of kilometers downward. Not small convection cells, planetary-scale currents, mass transport pathways spiraling through darkness. Unlike Earth, where convection is limited by a solid crust and mantle boundary, Jupiter's flows are unconstrained. There is no rigid lid. Energy rising from internal heat drives circulation continuously from the deep interior to the upper clouds. And this circulation interacts with metallic hydrogen below. Electric currents generated in deep conductive layers couple with convective motion above. Magnetic fields feed back into atmospheric flows. This is not just weather. It is a self-regulating engine. Hydrogen becomes metal. Metal conducts electricity. Electric currents generate magnetic fields. Magnetic fields influence convection. Convection shapes storms. Storms redistribute chemistry. And chemistry feeds back into thermal gradients. It is an endless loop. A planetary dynamo integrated from top to bottom. But perhaps the most unsettling revelation came not from lightning, nor from mushballs, nor even from magnetic anomalies. It came from gravity. As Juno passed close to Jupiter, tiny variations in its trajectory revealed how mass is distributed inside the planet. If Jupiter had a compact, but solid core made of rock and metal, a dense nucleus at the center, gravity data would show a clear concentration of mass. It did not. Instead, the gravitational field suggested something diffuse. Heavy elements were not confined to a small central sphere. They were spread out, mixed into surrounding layers. This led scientists to a startling conclusion. Jupiter may not have a clearly defined solid core at all, or at least not one that remains intact. The fuzzy core hypothesis proposes that heavy elements, rock, ice, metal, are blended into the metallic hydrogen region across tens of thousands of kilometers. Rather than sitting neatly at the center, they are partially dissolved, suspended, and redistributed by convection. This means the boundary between core and mantle, a concept familiar on Earth, may not exist in the same way on Jupiter. There is no sharp line, no stable nucleus, only gradients. Gradual transitions from heavier material to lighter hydrogen. And this structure may have originated in violence. Computer simulations suggest that early in the solar system's history, Jupiter could have been struck by a protoplanet nearly the size of Earth. The impact would have been catastrophic, not enough to destroy Jupiter, but powerful enough to disrupt its forming core. Fragments of that core could have been dispersed upward by convection. Metallic hydrogen, capable of dissolving heavy elements under extreme pressure, would gradually incorporate those fragments into surrounding layers. Over billions of years, the once solid nucleus would blur into a vast mixed region. Not fully dissolved, not fully intact, but unstable. And astonishingly, this mixing process may still be ongoing. If so, Jupiter is not a finished planet. It is a world still rearranging its interior, still redistributing mass, still evolving. That realization changes how we think about planetary formation. For generations, textbooks described gas giants forming around a solid core that accretes gas, then remains stable thereafter. Juno suggests something messier. Formation may not produce permanence. Cores can fragment. Heavy elements can migrate. Interiors can remain dynamic for billions of years. Jupiter becomes less like a frozen monument to the early solar system and more like a living archive. A place where primordial violence left scars that still shape the present. And this has implications beyond our solar system. Thousands of gas giants have been discovered orbiting distant stars. Hot Jupiters, warm Neptunes, super Jupiters. If Jupiter, our nearest gas giant, possesses a fuzzy core and evolving interior, then how many exoplanets share similar structures? How many worlds we classify as gas giants are in fact unstable mixtures of metal and hydrogen still reshaping themselves from within? Jupiter may be a template, or it may be an exception. But without Juno, we would not even know to ask. And here is the philosophical twist. For centuries, stability has been equated with solidity. We assume that strength means rigid structure, that permanence requires hardness. Jupiter suggests the opposite. Its immense magnetic field, its stable polar vortices, its centuries-long storms, all arise from fluidity, from motion, from instability sustained by energy. There is no fixed heart holding it together. There is circulation, there is mixing, there is constant transformation. Jupiter is stable because it is dynamic, because its interior never rests. And that forces a final question. If the largest planet in our solar system is still unfinished, if its core is blurred and its interior flows endlessly, what does that say about planetary systems beyond ours? About gas giants orbiting other stars? About the violent early days of solar system formation? Jupiter may not just be a planet to study. It may be a laboratory, a grand experiment running for 4.5 billion years. And we are only now beginning to read its data. But to understand its full significance, we must zoom out. Because Jupiter does not exist in isolation. Its gravity shaped the architecture of the solar system. Its mass influenced the formation of Earth. Its presence altered the fate of countless smaller bodies. To truly understand Jupiter is to understand the blueprint of how worlds are born. Jupiter is not quiet. It only appears that way from a distance. From Earth, it is a steady point of light. Pale, calm, unthreatening. Through small telescopes, we see bands and a red oval, beautiful, predictable. But beneath that calm exterior lies something immense, a machine that has never stopped running. Jupiter is not merely a gas giant. It is a gravitational architect, a thermal engine, an electromagnetic generator, and perhaps most importantly, a memory of the solar system's birth. 4.5 billion years ago, the early solar system was not orderly. It was not stable. It was a swirling disk of gas, dust, and debris. Protoplanets collided violently. Worlds were assembled and destroyed in the same epoch. Jupiter formed quickly, faster than any other planet. Its immense gravity allowed it to capture vast amounts of hydrogen and helium before the solar nebula dispersed. And in doing so, it altered everything. Its gravity sculpted the asteroid belt. It influenced the migration of Saturn. It may have prevented or redirected planetesimals that would otherwise have bombarded the inner planets even more catastrophically. Some scientists argue that Jupiter acted as both shield and destabilizer, deflecting comets away from Earth while also sending others inward. Without Jupiter, Earth's history may have unfolded differently. The presence of oceans, the frequency of impacts, even the timing of biological evolution, all may have been shaped, in part, by this massive neighbor. But Juno has shown us that Jupiter is not just a relic of the past. It is active. It still radiates heat left over from formation. It still churns metallic hydrogen thousands of kilometers below its clouds. It still reshapes its magnetic field. It still hosts storms that outlive human civilizations. It is not frozen in time. It is evolving slowly, continuously, relentlessly. And that forces us to confront a deeper implication. If Jupiter, the largest planet in our solar system, does not have a clean, solid core, if its interior is diffuse and dynamic, if its magnetic field shifts because conductive oceans of hydrogen flow in darkness, then perhaps our assumptions about gas giants everywhere need revision. Thousands of exoplanets have been discovered orbiting distant stars. Many of them are gas giants. Some are larger than Jupiter. Some orbit closer to their stars than Mercury orbits the Sun. We call them hot Jupiters. We model their interiors based on simplified versions of our own giant planet. But what if they, too, possess fuzzy cores? What if their interiors are even more chaotic? What if metallic hydrogen flows differently under more extreme irradiation? What if their magnetic fields reshape their atmospheres in ways we do not yet understand? Jupiter becomes more than an object of curiosity. It becomes a template, a laboratory where physics operates under conditions impossible to replicate on Earth. Pressure tens of millions of times greater than atmospheric levels. Temperatures capable of altering matter into exotic states. Global-scale convection unimpeded by solid crust. Rotation so rapid that chaos crystallizes into geometry. And here is the most humbling realization of all. The deeper we look into Jupiter, the more we realize that it challenges the idea of boundaries. There is no clear line between atmosphere and interior. No sharp division between core and mantle. No simple symmetry in its magnetic field. Everything blends, everything interacts, everything flows. Jupiter teaches us that planets are not static spheres with neat layers. They are systems. Integrated, dynamic, interdependent. Its storms are not isolated weather events. They are expressions of deep thermal currents. Its polar vortices are not decorative anomalies. They are products of rotation interacting with internal energy. Its magnetic field is not a passive shield. It is generated by invisible metallic rivers in perpetual motion. Its lightning is not superficial spectacle. It is a symptom of deep instability. Its mushballs are not curiosities. They are mechanisms of vertical chemical transport. Every phenomenon connects to another. Pull one thread, and you find it woven through the entire planet. And perhaps that is the greatest revelation Juno has given us. Not just data, but perspective. Jupiter forces us to abandon simplicity, to accept that planetary formation is messy, that cores can dissolve, that stability can arise from motion, that structure can emerge from chaos. In many ways, Jupiter resembles the early Earth, not in composition, but in principle. Earth, too, was once molten, bombarded, more unstable, layered through violent differentiation. Our world eventually cooled enough to support oceans and life, but Jupiter never cooled in the same way. Its mass trapped heat. Its hydrogen never condensed into rock. Its interior remains fluid and active. It is a world perpetually in between. Not a star, not a terrestrial planet, not fully solid, not fully gaseous. A transitional object that reveals what happens when gravity dominates chemistry. And there is something poetic in that. Because humanity's quest to understand Jupiter mirrors our quest to understand ourselves. We are products of the same protoplanetary disk, the same gravitational collapse, the same primordial chaos. By decoding Jupiter's structure, we decode the conditions that shaped the early solar system. By studying its fuzzy core, we rethink how planets assemble. By mapping its magnetic field, we learn how internal energy can shape entire space environments. By watching its storms endure for centuries, we confront timescales beyond human comprehension. Jupiter is not simply a planet we observe, it is a mirror held up to cosmic history, and it reminds us of something profound. The universe is not built from stillness. It is built from motion, from compression, from transformation, from energy that never fully dissipates. Juno did not just fly past Jupiter. It peeled back layers of assumption. It showed us that beneath familiar bands of clouds lies a world more complex than we imagined, a planet whose heart may have been shattered, whose interior remains fluid, whose magnetic field drifts, whose storms plunge into darkness, and whose existence shaped the architecture of our entire planetary neighborhood. Jupiter is no longer just a striped sphere in textbooks. It is a grand cosmic laboratory, a place where the laws of physics operate at extremes, a world that refuses to be simplified. And perhaps, as future missions venture deeper into the outer solar system, and as telescopes peer at gas giants around distant stars, we will discover that Jupiter was not an outlier. It was a prototype. The closer we look at Jupiter, the more we realize we are looking at the blueprint of how worlds are born.